In the previous video, we discussed Euler-Lagrange equation. d by dt, dl by dqs of I dot minus dl by dqs of I equals 0. This is called the generalized force. It is the true definition of force. And this is called the momentum canonically conjugate to q's of I. It is the true definition of momentum. For instance, you can check it for classical mechanical definition of Lagrangian. L is kinetic energy minus potential energy. Let's consider a particle moving in x direction only. So for this particle, q's of I is x. So Lagrangian is half mv squared. V is x dot. So half mx dot squared minus u's of x. So dl by dq's of I is x dot is half m. When you differentiate this, it's 2x dot minus u only depend on x. It doesn't depend on x dot. So it is 0. So pi of x is mx dot, which is momentum. However, let's not be prejudiced by what you have previously known to be momentum and force. This is the true definition of them. Pi of I, which is momentum, is dl by dq's of I dot. And force is dl by dq's of I. In this video, we are going to look at symmetries and connection between symmetries and conservation laws. Let's consider a bunch of particles interacting with each other in space. Now, nothing changes if you shift this bunch of particles from this location to some other location. Nothing changes even if you rotate them in the space and started them off at the same time. This is the nature of space. The properties of space is similar everywhere. If you do an experiment here or do it somewhere else, the results will be the same because space is the same. Similarly, nothing changes in the results of an experiment whether you do it today or do it tomorrow, because nature of time is same everywhere. This quality of time is a symmetry. It is called the time transitional symmetry. Why these symmetries are important to notice? What is the relationship between symmetries and conservation laws? Conservation of momentum and conservation of energy. Let's consider a trajectory of a system in space, time. Q's of I is the generalized coordinate and t is time. And this is the trajectory from t1 to t2. Let's consider you transform this trajectory in space. It can be moved or rotated in q's of I. But the form of the trajectory is not deformed. Like in the case we did on Euler-Lagrange equation, here also, a point on this trajectory can be characterized by q's of I bar. We can shift this trajectory a little bit by adding it to another function f of I and multiplied by a factor called alpha. So q equals q of I bar plus alpha times f of I. So if we differentiate this with respect to time, q dot is q bar dot plus alpha times f dot. So as we did earlier, dq by d alpha from here is f of I, and dq dot by d alpha is f dot. So the action of this new trajectory can be written as integral from t1 to t2 dt of Lagrangian, which is depending on q's of it and q's of I t dot. So once again, if we differentiate action with respect to alpha, dA by d alpha is summed over I integral from t1 to t2 dt dl by dq's of I times dq's of I by d alpha plus dl by dq's of I times dq's of I by d alpha. dq by d alpha is f of I and dq's of I dot by d alpha is f dot. So this can be once again written as summed over I integral from t1 to t2 dt dl by dq's of I f of I plus dl by dq's of I dot times f dot. We need to change this to f's of I as we did previously. But notice, this time the new trajectory does not pass through the initial points. Therefore, the endpoints must be considered. So how we did that? So if we differentiate a function f d by dt and integrate it once again indefinitely with respect to t, we get the function back. But if this is definite integral, then the result is function evaluated from t1 to t2. So if this function f is f times g, then this can be written as integral from t1 to t2 dt f times g dt. If you use chain rule for this, this can be written as integral from t1 to t2 differentiation of f df by dt times the other function g dt plus integration from t1 to t2 f time dg by dt. So this is equal to f times g evaluated from t1 to t2. So if you rearrange this, integral from t1 to t2 f times g dot is equal to minus evaluated from t1 to t2 f dot g plus fg evaluated from t1 to t2. So if we use this to substitute here, so this becomes differentiation of this part, that is d by dt dl by dq of I dot times undifferentiate this function f of I dt, and here we have to add the endpoint contributions plus summed over I fg, that is dl by dqs of phi dot times f of phi, evaluated from t1 to t2. So dA by d alpha is summed over I, integral from t1 to t2 dt. We'll take f's of I out of these two. So bracket dl by dqs of I minus d by dt dl by dqs of I dot f's of I plus summed over I dl by dqs of I dot f's of I evaluated from t1 to t2. When alpha reaches 0, this is 0. And because this trajectory is identical to the original trajectory here, because original trajectory satisfies Euler-Lagrange equation, this part is equal to 0. So this is Euler-Lagrange equation. Because this is equal to 0, then this part has to be equal to 0. So summed over I dl by dqs of I dot f's of I evaluator from t1 to t2 is equal to 0. This also can be expanded as dl by dqs of I dot f's of I from t2 minus dl by dqs of I dot f's of I from t1. So the function at t1 minus function at t2 is equal to 0, summed over I. That means these two parts has to be equal. But these are two quantities at two different times. And t1 and t2 are arbitrary points. So this has to be true for any t1 and t2 we consider. So for this to be equal for all t1s and t2s, the quantity dl by dqs of phi dot times f's of phi has to be a constant. In other words, this quantity has to be conserved. dl by dqs of phi dot is pi's of phi. So summed over I, pi's of phi, f's of phi is C. This is called Noether charge. To understand what this means, let's consider a trajectory of a system moved along x-axis. So this is x-axis, this is t, and this is the trajectory. It is characterized by q's of I bar. So to transform this, what we do, we add to that another function f's of I multiplied by alpha. So this is new trajectory, so characterized by this point q's of I. Now, what does f's of I means here? F's of I means the trajectory is moved in x direction without deforming it. Alpha corresponds to the amount of movement or the magnitude of the change. So pi's of x, f of x is conserved, means momentum is conserved in transformation in x direction. So in x direction, momentum is conserved. If we consider rotation of a trajectory around origin, so this is x-axis, this is t, this is the trajectory, and this is the rotation of the trajectory without deforming around the origin. Here, if f sub phi means rotation around the origin and alpha corresponds to the amount of rotation, then in the similar way, pi of theta, f of theta is conserved. This means around the origin, angular momentum is conserved. Pi of phi, f of phi is a constant, means the momentum is conserved. Why does momentum is conserved? Momentum is conserved due to transitional invariance. Okay, now let's look at the significance of time transitional invariance. So let's consider a coordinate system q of phi, and this is t, and this is the trajectory t1 to t2. Let's consider moving this trajectory upward in time by an amount epsilon. So what we do is we add an amount epsilon of t to this trajectory, and the new trajectory is characterized by q of I. So q of I equals q of I bar plus epsilon, which is a function of t. Now, due to time translational invariance, whether this action of the system take place now or some other time, it doesn't make a difference. Therefore, for the new moved trajectory, the action is the same. So action of this trajectory is t1 to t2 dt Lagrangian, which is a function of q's of it and q's of it dot. So for the new trajectory, the action is A is an integral from t1 plus epsilon to t2 plus epsilon dt of the Lagrangian. This Lagrangian depends on q's of it and q's of it dot as previously, but because this moves up and down in time with the change of epsilon, let's consider that this trajectory also explicitly depends on time. So we'll add t here. So if we differentiate this Lagrangian dl by dt, we can write it as dl by dq times dq by dt plus the second part dl by dq dot times dq dot by dt plus partial differentiation of this part dl by dt. So if you consider this partial differentiation of Lagrangian with respect to t dl by dt, this is different to this because this is partial differentiation only. So to make this something familiar, I am going to add here d by dt dl by dq dot and deduct once again the same d by dt dl by dq dot. So adding something and deducting the same thing doesn't make a difference. So dl by dq, I will take dq by dt out of this. So what is dq by dt? It is q dot plus this part dl by dq dot times dq dot by dt. dq dot by dt is q double dot plus partial derivative of Lagrangian with respect to t. So I will factor out this part dl by dq minus d by dt dl by dq dot, which is familiar to us, times q dot plus d by dt dl by dq dot times q dot plus dl by dq dot times q double dot plus dl by dt. So if we look at this part here, d by dt dl by dq times q dot. So if you differentiate this, the answer is dl by dq times q double dot plus d by dt dl by dq times q dot. So if you look at this, this is the same thing. So this can be replaced with this. So if you write everything once again, dl by dt is dl by dq minus d by dt dl by dq dot times q's of I dot plus d by dt. Now this one dl by dq q dot plus dl by dt is 0. Now if you look at this part, because this trajectory is identical to the original trajectory and original trajectory satisfies the principles of least action, this has to be equal to 0. So therefore we can rearrange this and write down d by dt dl by dq times q dot minus, we will take this part here, dl by dt. And what about this part, dl by dt? Because time transitional invariance, this new function is not explicitly depending on time. Therefore, dl by dt is 0. Therefore, this is equal to 0. So if we take d by dt out, dl by dq times q dot minus Lagrangian is equal to 0. In other words, dl by dq q's of I dot minus Lagrangian is conserved. dl by dq is pi's of I. So pi's of I q dot minus Lagrangian is a constant and it is called hamiltonium. This is the Hamilton's equation. This h is also the energy. In fact, this is the definition of energy. What this shows is, due to the time transitional symmetry, energy is conserved. Once again, let's not be prejudiced by what you have previously known as energy. In these two videos on Euler-Lagrange mechanics, we have been particularly looking at functions, maxima and minima of functions, and some particular conditions in which functions are stationary. These are pure mathematical apparatus. Momentum, pi of I is dl by dq dot. The generalized force is dl by dq of I. And Hamiltonium energy is pi of I q dot minus Lagrangian. These are names we have given to some parts which we consider to be important to consider. In the next video, we'll get back to relativity and use these apparatures we created to understand energy, momentum, and matter. Subscribe to this video channel because this is going to be a comprehensive course on special theory of relativity and the nature of time. You can download this lecture note from the link given below.